Do you find me attractive? Says one molecule to the other. If the answer is yes, they can form a solid or a liquid. If not, well, I guess you're going to be a gas. Now, here's a question that you don't normally see. I mean, very popular question over the last few years is water wet? Well, here's a question that's even more interesting. Why is water sticky? That's right. Water will stick to pretty much anything. Now, there are certain surfaces like something that's been freshly waxed that the water will just simply beat up and slide off of. But water is very sticky. Once it gets onto something, it tends to stick to it and make that thing wet. Two questions answered in one shot. All right. So, what are these intermolecular attractive forces and what causes them? Well, remember, gas molecules, if they're ideal gases, have no attractive forces between them at all. Solids have strong attractive forces, and liquids have moderate attractive forces. Heat of fusion is the heat you add to weaken a solid's attractive forces to turn it into a liquid. Heat of vaporization is the amount of heat you have to add to completely destroy a liquid's attractive forces and turn the substance into a gas. It's caused by the attraction of oppositely charged ends of different molecules. This is why it's called intermolecular. It's molecular attractions between different molecules. So the positive end of one molecule and the negative end of another molecule, or more specifically, the partially positive end of one molecule, will attract to the partially negative end of a different molecule. Much in the same way, dogs' noses always seem to be attracted to other dogs' butts. I'm just grateful that we came up with the fist bump. The stronger the attractive forces, the greater these partial charges are, the more energy it's going to take to melt and boil the substance, and the less likely it's going to be to evaporate. These attractive forces are also responsibility for the ability of substances to dissolve into solvents. For example, substances with very weak attractive forces don't give water anything to grab onto, and so typically will not be soluble in water. These would include things like oil. And this is going to come down to the polarity of the molecule. So, what causes these attractive forces is this polarity of the molecule. Polar molecules have partially charged poles, and they can very strongly attract each other, although the electronegativity difference will determine just how strong that attraction is. So, again, like one dog sniffing another dog's butt. Nonpolar molecules have no permanent poles. They have temporary poles that's caused by electron motion in the molecule. I'll show you an example of that later on. This leads to very weak attractive forces, kind of like birds that just fly wherever the heck they want. In fact, birds would have stronger attractive forces than even a gas would have. First, let's take a look at the shape of a molecule, because the shape is going to determine how polar a molecule is. Now, you're going to learn about more shapes than these basic four if you move on in chemistry. But for the purposes of this course, we're going to examine the four basic shapes that a molecule can have. Linear. Linear molecules have two atoms in them. It is also possible to have a three-atom molecule, like carbon dioxide, that's linear. I'll show you an example of that in a little bit as well. The idea here is the atoms are arranged in a straight line. Bent molecules have three atoms where the other atoms are bonded at an angle due to the position of the valence electrons. Water molecules and hydrogen sulfide molecules are bent. Pyramidal molecules are ones that have four atoms. One of the atoms is in the center, and the other three radiate outwards from the center. Ammonia and phosphorus trichloride are examples of pyramidal molecules. And tetrahedral molecules have five atoms, one in the center and four radiating out from the center, like methane and tetrachloromethane. These are very simple molecular shapes. You'll learn about more complicated shapes if you take a more complicated chemistry course, but this will suffice for now. So linear, bent, pyramidal, and tetrahedral. The shape, of course, is determined by where the unpaired valence electrons are. In oxygen, the unpaired electrons are here, and so that's where the hydrogens bond. In nitrogen, the unpaired electrons are here, here, and here, so that's where the hydrogens bond. And in carbon, the unpaired electrons are here, 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 and here, so that's where the chlorines bond. So the shape is dependent upon those valence electrons. There is another consideration. Again, if you take a more advanced science class, you'll learn about valence shell electron pair repulsion theory, which will refine these shapes a little further. But we're not going to get into that in this level course. The dot diagrams. In order to get the dot diagram for a molecule, you simply need to replace each dash, which represents a covalent bond, with the pair of shared electrons that that bond represents. A pair is represented as two dots. Two dots. Two dots, two dots, two dots, two dots, two dots, two dots, two dots per bond. Don't you get up and walk away. You're not done yet. Because remember, the entire purpose of bonding is so that each atom ends up with a stable octet, four pairs of electrons. Now, hydrogen only has one energy level, so it can only have two, but everything else had better end up with four pairs of electrons, a stable octet. For example, this chlorine already has one pair of electrons, so give it three more pairs, and now it'll have a stable octet. These chlorines are sharing one pair. Give each of them three more pairs, and they'll both have stable octets. This oxygen is sharing two pairs. Give it two pairs more, and there's a stable octet. Same with the sulfur. This nitrogen is sharing three pairs. Give it one more, and it'll have a stable octet. This phosphorus has three. Give it one more pair, and while you're at it, these chlorines are only sharing one pair. Give them three more pairs. Now every atom has a stable octet. Carbon has a stable octet. Hydrogen doesn't need it because it only has one energy level. Carbon has a stable octet, but these chlorines are only sharing one pair. Give each of them three more pairs, and everyone will have a stable octet. So drawing the dot diagram is relatively simple. What if there are multiple bonds? Well, this is no big deal because each bond is a pair of shared electrons, and therefore a double bond would be two pairs of shared electrons. Let's see, if one pair is two, how many would two pairs be? Four. Two pairs of electrons. And this carbon dioxide, remember I showed you, it's going to be linear. Here's the linear shape of carbon dioxide. Two pairs of electrons, two pairs of electrons. Replace those dashes with two pairs of dots. Now, what about the triple bond? Well, 2, 4, 6. So three pairs of dots. One pair, second pair, third pair. Replace each dash with a pair of dots. And again, don't get up and walk away because you're not done yet. You got to make sure to put in unshared pairs so that each atom has four pairs, including the ones that are being shared. These oxygens are sharing two pairs of electrons. Give each one two more pair. Now, why did I put them off at an angle and make this look like a TIE bomber from Star Wars? To keep the molecules symmetrical. And that's going to be important for the next step. These nitrogens are sharing three pair, so they each need one more pair, again on the ends to make the molecule symmetrical. The carbon is fine. It's sharing four pairs of electrons. It already has a stable octet, but these oxygens only have two pair each. They each need, just like in the first example, two more pair. It's like a stretch TIE fighter bomber thing. So that's how you do the dot diagrams for these molecules. All right, now on to molecular polarity. So we're going to put these examples back up here again. The first thing you need to do is figure out how symmetrical the molecule is, and we do this by creating lines of symmetry. A line of symmetry is an imaginary line where both sides of that line is a reflection of the other side. So, for example, if I were to take hydrogen and cut it that way, each side of that line is a mirror image. If I cut the hydrogen that way, each side is also a mirror image. So hydrogen has two lines of symmetry. This makes hydrogen a symmetrical molecule. For the hydrogen chloride, if we cut it this way, we have reflection on either side. Now understand, it's not the letter that we're interested in. It's the atom that that letter represents, the symbol represents. We cannot cut, like we did with H2, we cannot cut it down the middle vertically, because then the reflection will not be the same on either side. So with only one line of symmetry, HCl is a lopsided molecule. It's not symmetrical. It's asymmetrical. Putting an A in front means without, so HCl is without symmetry, and that will be important to determining its polarity. Diatomic chlorine has two lines of symmetry, two ways you can slice it where it's symmetrical on each side. Both H2O and H2S have only one line of symmetry, vertically. That's the diagonally, rather. That's the only way you can slice it so that you have a mirror image on both sides. So both water and hydrogen sulfide are lopsided asymmetrical molecules. NH3, can you cut it this way? No, because you won't reflect the H on the other side of that line of symmetry. The only symmetry ammonia has is straight up the middle. Same with phosphorus trichloride. What about methane? Well, methane has, you can cut it this way, or even diagonally. Methane has four ways that you can cut it so that it's a mirror image on both sides. Therefore, methane is a very symmetrical molecule. What about trichloromethane? Well, we have this 3 Cl's down here, but we have an H on top. So the only way you can slice it so it's symmetrical is straight up the middle. So that means that this molecule is lopsided. Now, what exactly do I mean by lopsided? Remember, we were talking about electronegativity and polar bonds? Hydrogen has an electronegativity that's less than chlorine, so the electrons are pulled towards chlorine, giving chlorine a slightly negative charge and hydrogen a slightly positive charge. The charge is lopsided towards chlorine. The electron distribution is lopsided towards chlorine. Two or more lines of symmetry, there is no lopsidedness to the charge distribution. Therefore, the molecule will have no charged ends. It will be nonpolar. So any molecule with at least two lines of symmetry will be a nonpolar molecule. These molecules will have very weak attractive forces. One line of symmetry means that the electrons are being pulled more in one direction than another. We call this a dipole, where one end of the molecule is partially positive and the other end is partially negative. Because of this asymmetrical charge distribution, any molecule with only one line of symmetry would be considered a polar molecule. It doesn't even have to live in the Arctic, because that would be a polar, bear. The dipole moment is showing you the direction that the electrons are being pulled along the single line of symmetry. So what you do is you look up the electronegativities of the bonded atoms, and the arrow goes towards the more electronegative atom. Now here's a little hint. Hydrogen at 2.2 has the lowest electronegativity of all of the nonmetals. And so if hydrogen is on one end of your line of symmetry, the arrow will always point away from the side with hydrogen. You can also put a little hash mark at the end to make the end look like a little plus sign. Because on the other end, the end the arrow is pointing towards, the more electronegative side is partially negative, and the less electronegative side is partially positive. And this demonstrates the lopsided nature, which means that if we have a molecule of phosphorus trichloride, if two of them happen to come close, the partially negative end of this phosphorus trichloride molecule will attract to the partially positive end of a different phosphorus trichloride molecule, thus giving you intermolecular attractive forces. Polar molecules have stronger attractive forces than nonpolar molecules. So, what are these attractive forces called? So, as the polarity increases, the attractive force strength increases. Polar molecules have what are called dipole attractions or dipole-dipole attractions, where the partially negative end of one molecule attracts to the partially positive end of another. These poles are permanent, they're always going to be there. When this molecule, partially negative end of one molecule will attract to the partially positive end of a different molecule. And that attraction that holds them together is called a dipole attraction. Nonpolar molecules can also attract each other, but not with permanent poles. Nonpolar molecules can form temporary poles. The electrons don't just sit still in a molecule, they slosh back and forth from atom to atom. And so over time, you can form temporary charges. If electrons happen to be sloshing more towards one side of the molecule than the other, then you're setting up a temporary asymmetry in the charge distribution. It's only temporary, though. The bigger the molecule is, the more electrons you have, and therefore the more charge will be built up by this sloshing back and forth. Let me show you a simple example of this sloshing back and forth. So let's just follow the path of one electron being shared between two hydrogen atoms. You can see that it sloshes back and forth in the molecule. But overall, there is no side that gets the electron more than any other. However, if we freeze frame it for this moment, when the electron is on this side of the molecule, for that instant, that side of the molecule is partially negative because the charge distribution has sloshed more towards the left side than the right side. Now, in the next instant, that electron has already moved to the other side. So these are only temporary charges, not permanent charges. If at that exact moment another molecule comes by that happens to have an orientation, this dot belongs over here. For that instant, you're going to get a temporary attraction between those molecules. Now, we call this attractive force the London dispersion force, and it's named for the fact that electrons are dispersed throughout the molecule. And because of their motion, there can be asymmetry that is temporary, momentary. Now, if the molecules are moving slow enough, then this attractive force may be all you need for a liquid or a solid. But you got to cool these down a lot to get them to melt, to freeze or condense. Most of these substances, especially the smaller molecules, will be gases. So if you have permanent poles, you have dipole attraction. If you have temporary poles, you have London dispersion forces. But there's one additional type of attractive force. Remember I mentioned how water has an unusually strong attractive force for its size? Well, here's why. Hydrogen bonding. Hydrogen bonding not only has a strong dipole attraction, these molecules are very polar, but they also form temporary covalent bonds between them. So here's one water molecule, and here is a neighboring water molecule, and we'll have an attraction between the partially positive end of one molecule and the partially negative end of another. That's the dipole attraction. But hydrogen bond takes it one step further. While the hydrogen of one molecule and the oxygen of another are in close proximity to each other, they can even form a temporary covalent bond between them. This makes the attractive forces between water molecules extremely strong, strong enough that you can actually place an insect on the surface of the water, and it will walk on the surface of the water. It won't just sink. There's surface tension to the water. This is why you can pour a cup of water higher than the rim of a cup, and it forms a meniscus. This is why water molecules climb up the sides of a graduated cylinder. This is why water molecules climb up the internal network of tubes inside any plant or tree. These attractive forces between water molecules make water a liquid when any other molecule its size would be a gas at room temperature. Water molecules are unique, and without them, we cannot have life as we know it. Hydrogen bonding has additional benefits as well. Hydrogen bonding is what holds the two strands together in DNA. And when it's time to replicate the DNA, you're not actually breaking a permanent physical bond, you're unzipping temporary bonds. And therefore, in transcripting the DNA, you have much less of a chance of making errors. Now, hydrogen bonding will happen in any molecule where you have hydrogen on one end of the molecule and either nitrogen, oxygen, or fluorine on the other end. Those are the only instances where hydrogen bonding will take place. So that's the surface tension of water. In the middle of the water, each water molecule is attracting to the surrounding water molecules, but on the surface, there are no water molecules above it. So the water molecules on the surface can have extra attraction for each other. And this allows bugs to walk across the surface of the water. And again, it also allows the double helix of DNA to form. You can see hydrogen bonds will appear between the base pairs. That is molecular shapes, polarity, intermolecular attractive forces. On the next video, I'm going to show you how to write the names and formulas for ionic and molecular compounds. Thank you for playing along, folks. Until next time, as always, bye.